We are now electromagnetic induction, page 615. First of all, we have understood the magnetic field and magnetic force, all that in previous chapters. Now we'll think, can we generate electric current using magnetic field? Yes, you can. Magnetic field can be used to generate electric current. There are magnets which approach the magnetic field B, it produces the current. Now look at figure 22.1, no current in the coil. Figure 22.1 again B, the current is created between magnetic lines as towards it turns to the coil. Now 22.1c, the current exists. Now it comes out. It's moving in the opposite direction as you see in the figure 22.1c. Now look at in this figure A. We have arrangement of coil here, and we have magnet, north pole, south pole. The coil is connected to a meter to read the current. Now slowly we move the magnet towards the coil. Then you will see there will be current being generated as the magnetic field moves, red lines. Then it goes closer and closer, the more current will be produced in the coil. Then we come back, what happens is slowly and slowly the direction of the current changes. As you move from the figure C, as you see, move from the coil slowly to your left side, the current direction is changed, it's reversed. The current in the coil is called an induced current. By changing the magnetic field, it's done by the induction. That's why the name is a little different. You will see later on. And then changing the magnetic field induces EMF in the coil, and it leads to induced current. As you see in this picture 22.3, page 616, when the area of the coil is changing, the induced EMF and the current will be generated. So both induced EMF and the current will be generated. Okay, the cross points, like you have marked in red, these are the magnetic field lines going onto the paper, and this is the coil you have connected to a ammeter to measure the current. So what happens here is, as you keep on changing the area of the coil, like you pull it, so the area changes, or you push it, area changes, it will generate induced EMF and the current will be there. Now the next topic is motional EMF, which is page 617, figure 22.4, where we'll see the conducting rod between two rods is moving from from left to right side in the magnetic field, and the magnetic forces causes to go the charges onto the other end of the rod, as you see. So this is known as the induced EMF, and causing to generate current I in this circuit. Now the moving conductor gives rise to an induced EMF. This is known as motional EMF. You can clearly see in this picture here, the rod is moving here, and there's a bulb which gets lighted. Slowly as it moves, your hand is moving, then you see the induced current is generated and the bulb will get lighted. But when it's stationary, is not moving, there will be no current generated to light the bulb. Now look at the figure we have 22.4, where you will see the velocity of movement, magnetic field, and the length of rod are mutually perpendicular to each other. Now the next idea is to compare the electric field with the magnetic field, rather I would say electric force with magnetic force. Now the electric force is not being seen here. We are just thinking that there will be electric force as per the electric field is there. So electric field E is the voltage divided by the length of the rod. That's what I show you here, voltage divided by length of the rod. And electric force is F, which is EQ, that equals to epsilon divided by L times Q. So electromotive force divided by L times Q. Then we have magnetic force equals B times Q times V times sine theta, which is 90 degree here, theta value wise. So we have B, Q, V. Sine 90 is 1. As I told you before, the electric field will be same as magnetic field. They will balance each other. So Xi here equals to B times L, which is induced EMF. Now let's go to the figure 22.5, page 618, and also please go over the example 2 you have exercise wise on page 619. This is your conducting rod. It moves through this line, two parallel lines of conducting rod also. This rod moves at perpendicular to the magnetic field lines. Initially x was 0 times 0, it becomes x and t when it moved to a distance x. With t, t0 changes to t, x0 changes to x. So we'll have an equation now. You will see that. Okay, now the induced EMF is equal to B times L. In the figure 22.8 as well as 22b, you have A and B both. The rod moves x0 and time is 0. In figure 22b, x is greater than distance wise when time is t. So x0 changes to x, t0 changes to t. So now the velocity will be distance over time, so it will be x minus x0 divided by t minus t0. Finally, you will reorganize the whole equation. So your induced EMF equals xl minus x0l divided by t minus t0 times b. Here in this picture you have the same thing as I was mentioning before, but picture is here. X0, t0, x and t. We will be arriving at this different equation now, which I told you before. Okay, xi we have to figure out. Now xl and x0l are area, x times length. So xi will be equal to a minus a0 over t minus t0 times b. So your induced EMF will be b times a here. So b times a minus b times a0 divided by t minus t0. The product of b times a and b0 b times a0 are called as the magnetic flux phi. Now go over the exercise which is 4 on page 623. This shows you when the magnetic field makes an angle theta to the normal, so it will be b cosine theta as you see in the red line in this picture. So the magnetic field, the component of the magnetic field that is perpendicular to the surface should be used as the component to be like b cosine theta or phi, whatever that angle is. Now we moving to Faraday's law. Faraday discovered that when there is a change in the flux, we already defined the flux, through a loop of wire, EMF is induced in the loop. Faraday's law of electromagnetic induction is expressed by changing together the magnetic flux as well as the time. So we can write the equation as you see, the induced EMF equals negative n. N is the number of turns or number of loops in the coil. Initial magnetic flux is 0 here. So phi, take away phi 0 over t minus t0. Now induced EMF equals negative n delta phi over delta t. The unit is volt here. Please go over example 5, page 625. The next topic we have is mutual induction. Refer to the figure you have 22.26. There you have a primary and a secondary coil. The primary coil is connected to AC generator, where we designate the current passing through the generators as IP. Secondary coil is connected to a voltmeter to read the volts. Look, the EMF can be induced in a coil which is secondary, moving the magnet nearby as shown in the picture or the figure. The primary coil and the secondary coil are placed close to each other. The primary coil is connected to an AC generator, as I told you. Again, I am telling you. And the coil which sends AC current is IP, and the secondary coil is connected to voltmeter. Okay, in this figure you have the alternating current is being generated in the generator here, and the changing field induces an EMF in the secondary coil. The changing field, I mean the changing field, which is a magnetic field, induces a EMF in the secondary coil. Effect in which a changing current in the circuit induces an EMF in the other one, which is in the circuit, is called a mutual induction. I'll repeat again. The effect when a changing current in the circuit induces an EMF in another circuit is called as mutual induction. So average EMF you can calculate in the secondary coil, in the primary coil, and change in the flux can also be produced by change in the current, which is IP. Let's say there are n number of loops in the secondary coil. So net flux in the secondary coil will be Ns, which is N secondary times the flux, which is magnetic flux. Again, N times magnetic flux will be proportional to IP, which is in the primary current. When there is a change in the equation, we can rewrite as Ns times flux, magnetic flux, equals to M times IP. M is a constant of proportionality, so we can define M as ns over ns times phi s over ip, or ns over ip times phi s, and m is defined to be the mutual inductance. Now let's substitute the equation in the Faraday's law, where the induced EMF equals negative ns times delta flux, magnetic flux rather, secondary divided by delta t. Then finally we simplify, we'll end up with negative m ip over t. So the induced EMF due to the mutual induction is equal to negative m, which is mutual induction, times delta p over delta t. The last topic we have is self-induction, which you can go to page 638. Here what happens is the alternating current in the excuse me, the coil generates an alternating magnetic field which induces EMF in the coil. It's a very simple one. This is the equation which is similar to the mutual induction, so please read yourself, and the example also there in the same page, which is page 638. Thank you.